Hi my friends, today's video is going to talk about logarithms, a little bit about what a logarithm is, how to evaluate logarithms, what some special logarithms are, how to estimate logarithms, and when given a bunch of logarithms, how to put them in order from least to greatest. So there's a lot going on in this video. Feel free to fast forward and skip over parts you feel comfortable with, or slow down and rewind things you need to hear a couple more times. So in class, we started not by using logarithm notation, but by using this notation STM. And so we started with like STM 3 to 27, and how would we figure that out? And we talked about how this little number here represented what you were multiplying by. So STM 3 meant you were making your number line starting with a 1. We're always starting with a 1. And then multiplying by 3. And we could keep going on and on forever. We also talked about how you can extend the number line to the left, and there we would need to divide by 3. So we're not going to get negative 3, but we would get negative 1, we would get 1/3, 1/9, 1/27. And we talked about how staying away from a calculator is probably a good idea. Once we have these numbers to the right, 3, 9, 27. To the left, we just have 1/3, 1/9, 1/27. Okay. We made lots of connections about how 3 to the 0 power would be 1, 3 to the first power would be 3, 3 to the second power would be 9, 3 to the third power would be 27. And same thing here, this would just be 3 to the -1, -2, -3. We also talked in terms of jumps. So if we said we're trying to figure out STM base 3 of 27, that means starting from 1, how many jumps does it take to get to 27? Well, it would take 1, 2, 3 jumps, which is where this 3 as an exponent comes from for 3 to the third power. Then towards the end of today's lesson, we talked about how STM is not a real mathematical thing. Well, the thing is real, but the notation STM is not. Instead of using STM, we are going to use the word logarithm. So you will see problems that don't say STM base 3, but log base 3 of 27 equals 3. And we're not going to let the log scare us. We were great with STM, so we will be equally as great as with logs. In our logarithm, we will always have 3 numbers or variables. The b, the little tiny subscript, represents the base, and it is what we are multiplying by. So when we go to make our number line, we'll always start at 1. And then the b will indicate what your next number is based on what you're multiplying by. X, we talked about, is where we land. Where we land on the number line after taking a certain number of jumps, and that number of jumps is y. So y is the number, that's not a hashtag, it's a number symbol, number of jumps starting from 1. And we've done problems where kind of the thing we're trying to find can be any of those 3 things. So maybe the box was here and you were trying to figure out what x was, or maybe the box was around y and you were trying to figure out what y was, or you can know x and y and maybe the box is around b and we're trying to figure out what b is. But those 3 things, little number, our tiny subscript, is the base, x is where we are landing on the number line, and y is the number of jumps. So the number of jumps is the thing we're trying to find. It's the output. Okay, so if we have something like this where we're evaluating a logarithm, well, in all of these logarithms, we're given the log, we're given the base, we're given the where we're trying to get, and the thing we're trying to find is how many jumps do you take. So when we evaluate a logarithm, the question's really asking how many jumps on the number line starting from 1 is it going to take to get there. So for each of these, you can make a little number line, and as you get going, you might get a little better and feel like that you can do it mostly in your head. But remember, our number line is going to start at 1, and I usually go in the positive direction first. And for this problem, I'm multiplying by 5. So my next number would be 5. And then if I multiplied by 5 again, my next number would be 25. And if I multiplied by 5 again, my next number would be 125. So this number line is modeling base 5. And now we're just counting, starting from 1. How many jumps does it take to get there? 3. So if you do not know or you can't tell just by looking at something, you can always, always, always make a number line to help you. And just make sure when you make your number line, we're starting from 1 and we're either going to the right or to the left depending on what you need. So if you're trying to find a fraction is where you're landing, you're going to probably have to go to the left. But in this case, for this next problem, we're multiplying by 6. So 1, 6, 36, 216. And we're trying to figure out from 1, how many jumps does it take to get to 36? 2. And you'll notice as you go, maybe you don't need to make the number line for some problems, and for some problems you do, but the number line doesn't take really long to make and can always be your fallback option. We also talked in the number lines about how the numbers really shouldn't be evenly spaced. Yes, it's scrap paper for you to use, and no judgment. It's really hard to make it go all the way to 216, but we did talk about in class how since this is growing exponentially, the difference in between is not the same. So here we had a difference of 5, here we have a difference of 30, here we have an even bigger difference. So as we keep multiplying by 6, the numbers are going to get farther and farther apart. Our third one's a great example of needing to go to the left on our number line. So I still, even though I know I need to go to the left because 49 is to the left, I think it helps to go to the right first. So I'm going to start multiplying by 7, multiplying by 7. And now when I go to the left, I'm going to divide by 7. So that's going to give me 1 over 7, 1 over 49. And these numbers to the left will always have kind of a pair with a number on the right. So if the second number to the right was 49, well, the second number to the left is 1 over 49. So starting from 1, I'm going to take 2 jumps to the left to get to 1 over 49, and I'm going to indicate that I went to the left using -2. If I put 2, that would be incorrect because 2 jumps would get me to positive 49. Okay, here, log base 8 of 1. So I'm making my number line, again, always starting at 1. Here I'm multiplying by 8. 1 times 8 is 8. 8 times 8 is 64. Keep going and going. And if I'm starting at 1 and I want to land at 1, well, that means I didn't jump at all. So I took 0 jumps to get to 1. And this is a common property, right? Because no matter what the base is, if I'm trying to land at 1, it's always going to be 0 jumps because 1 is where you start from. So this is kind of a property that we have that we can say when we're taking a logarithm, no matter the base, if we're trying to land at 1, it's going to be 0 jumps. And this second one here, or this last one here, but second one of these two, is another common property. So here we're starting at 1 and we're doing a base of 9. So 1 times 9 is 9, 9 times 9 is 81. And the question is, how many jumps does it take me to get to 9? Well, since 9 is what we're multiplying by, it's going to be 1 jump. So our second kind of common property is if we're taking a logarithm and we're trying to land at the number that is the base, right? Log base 9 of 9. Same thing if we did log base 5 of 5. Well, that would mean we'd make a number line and we're multiplying by 5s. And to get to 5 is still going to be 1 jump. Okay. So log base b of b is always going to equal 1 is another common property. Just to have, you can always again make the number line, but something that should stand out to you as a common pattern. Okay, so when we're evaluating, that means we're always given the base and where we land, and we're trying to find the number of jumps. Before we move on to the next part, which is going to be, let's say this box kind of moves around and I'm trying to find something different. But before we do that, we want to talk about 2 special logarithms. So there's 2 logarithms that have different notation, and that is base 10 and base e. So base 10 is called the common logarithm. And basically what that means is that oftentimes you'll see problems where there's not a little subscript. So it'll just say log of 1,000. And sometimes students are like, wait, how do I know what I'm multiplying by? The little base is missing. Well, if the little base is missing, it is assumed to be 10. And so we don't usually write it. You don't normally see people write log base 10 of 100. Instead, they would just write log of 100. So if there's no base there, it's 10. So if you want to write it in, that's fine. But if you ever see a problem, it's not that I forgot to type the base, it's the base is 10. Okay, we kind of talked about this when we talked about square roots, right? Like this is a cube root, this is a fourth root, but we don't actually write a 2 here, even though that's what a square root means. So same thing for logarithms. If there's no number there, it's assumed 10. So just to do an example problem, if we said, okay, well, what's log of 1 over 100? Well, that would mean I'm going to make my number line starting at 1. And then you're like, okay, what do I multiply by? Well, there's no number there, so that means we're multiplying by 10. So 10, 100, 1,000. But if I want to get to 1 over 100, 1/10, 1 over 100 would be 2 jumps to the left, so it would equal -2. Okay, so first one, special one, is the common logarithm, which is if there's no tiny base there, it means it's base 10. The second common logarithm, or logarithm that has special notation, is when the base is e. And remember from last week, e is a number, similar to how in geometry you talked about pi being equal to about 3.14 with a whole bunch of decimals. E is a number and it's equal to about 2.718, or sometimes people say 2.72. Okay. And if we had log base e, it would just mean we're starting at 1 like we always do. And we're going to multiply by e every time. So our second number would be e, which is about 2.72. And then we would multiply by e again and get some decimal. And then we would multiply by e again and get some decimal. So usually for e, instead of writing 1e and then writing all the decimals, we just write e squared, e cubed, right? Because this is 1 times e times another e, so that would be e squared, times another e, so that would be e cubed. And then if we were going to go the other way, it'd be 1 over e, 1 over e squared, and so on. So e is our special number, 2.718. The e stands for Euler. It's the mathematician's name. It's Euler's number. And if we're doing a logarithm with base e, rather than writing it like so, it has its own special notation, and you'll see it on your calculator, which is ln, which stands for the natural log. And so the natural log, ln x equals y, just is telling you that your base is equal to e. So when you make your number line, you're multiplying by e every time. Okay, so summarize this. If you see a logarithm with no base, the base is 10. And if you see ln, it stands for natural logarithm. It's Latin, I believe, which is why it is backwards. But some of you who are Spanish speaking and speak other language, you notice that we flip them. So ln stands for natural log, and that would just mean the base is e. Okay, so let's go to some filling in the blanks. And I'm going to just add one that uses some of those. Log of 10,000. And let's do, sorry, 2 seconds. Oh, nope. Natural log. Okay. So filling in the blank means the blank could be in any of our 3 spots. It could be in the base, it could be in the number we land, or it could be in the jumps. So let's remember that base, this is number we land, jumps. So I'm just going to put some shorthand, jumps. Where we land on the number line, what we multiply by to make the number line. So for this first one, we know the base. We know we're multiplying by 12, so I can make my number line multiplying by 12. 1 times 12 is 12. 12 times 12 is 144. I could go the other way. 1 over 12, 1 over 144. And I also know that I'm taking -2 jumps. So that means I'm starting from 1, I'm going 2 jumps to the left. So that would get me at 1 over 144. Okay, for the next one, log base 11 of 11. So I know I'm multiplying by 11 by the little 11 there. So 121, could go the other way, 1 over 11, 1 over 121. And I'm trying to land on 11. So from 1 to land on 11 would be 1 jump. Okay, moving along. Here, I don't know my base, so I can't really make my number line because all I know is that there's a 1 on it. But I know that if I take 2 jumps, I need to land on 25, right? So this is saying 2 jumps to land on 25. So what would I had to have gone by? Well, I would had to have gone by 5. That way 1 times 5 is 5. 5 times 5 is 25. So 2 jumps to get to 25 means I must have been going by 5s. My base must have been 5. Coming up next, I have a base of 7. So that means I'm going 1, 7, 49. I need to get to 1/7, so I'm going to go the other way. Well, coming next will be 1/7, 1 over 49. So using base 7, starting at 1, to get to 1/7 is going to be negative 1 jump to the left. Okay, just 2 more. So here I know I'm going by 6s. So 1, 6, 36, 216. You could keep going. I would need a calculator. And the 3 means I'm not trying to get to 3. Remember, 3 is the number of jumps. So 3 jumps, 1, 2, 3, means I'm going to land on 216, which is what I was trying to figure out. And then here are my last 2 we added on. So there's blank. This is blank too, but we know what it is. Remember, if there's nothing there, it means it's a 10. So 1, and then I'm going by 10s. Times 10 is 100. Sorry, 1 times 10 is 10, times 10 is 100, times another 10 is 1,000, times another 10 is 10,000. So how many jumps was that? That's what I'm trying to figure out. 4 jumps. And then last but not least, natural log, which is usually people think it's the trickiest just because they're like, I don't know what this is, E's a decimal, but let's not make it super hard. So I'm always starting at 1 right on my number line. And natural log means the base is E. So imagine there's a little E subscript. So I'm multiplying by E, which would get me to E, or 2.718. But then if I multiply by another 2.718, I'm going to get a gross decimal. So I'm just going to write E squared. And then if I multiply by another 2.718, I'm going to get another gross decimal. So I'm just going to write E cubed. So when I write my number lines for E, it's really common to, instead of seeing the actual numbers, to just see 1, E, E squared, E cubed, right? Which is really what we're doing anyway. This is 1, 7 to the first, 7 to the second, right? This was 1, 10 to the first, 10 to the second, 10 to the third. But we actually found what those values were. For E, because they're going to be decimals, we're just going to leave it. E, E squared, E cubed. If I was going to go the other way, it would just be 1 over E, 1 over E squared, 1 over E cubed, and so on. So 2 is the number of jumps. So starting from 1, I'm going to take 2 jumps. That's going to get me to E squared. So I'm going to just write it a little nicer down here. So basically we're saying natural log of E squared is equal to 2, which is saying if my base is E and I take 2 jumps, I'm going to get to E squared. So I'm going to pause here just so this video ends, and that finishes up evaluating and filling in blanks. And if you would like, part 2 of this video is going to talk about how to estimate. So what if the number isn't on the number line, and how, if you're given a bunch of logs, how you can put them in order to least to greatest. So if you are interested in that or need help with that, stay tuned for the second video. See you soon.